All right, guys, this is hopefully your last video from me for this unit and possibly for remote learning. Maybe you'll be seeing my face in person. We are going to do the last bit of notes for this unit called Free Fall Up and Down Problems. So hopefully you already watched the video about free fall motion. These are instances where the initial velocity of the object is not zero. So before you were talking about objects that were dropped, they were just let go from rest. But I don't have to just let go of an object. I could throw it down. I could toss it up. There are a few different ways, and I small gifts here because I just love them so much. Just to illustrate my point. This thing that's blocked by said gifts, it says all uniform acceleration equations still apply. So that other video that explained those 4 equations with acceleration and all that stuff, you can still use that here because the acceleration of gravity is always negative 9.8 as long as we are on Earth, and that does not change. Cool. Stuff to keep in mind, whenever something is tossed up, which is we talk more about tossed up things than thrown down. So things that are tossed up make a kind of parabola shape. And parabolas are symmetric, meaning if you fold them in half, they're the same on both sides. So that's what this statement is saying. There is symmetry in the motion of a ball that is tossed up and then falls down. So the acceleration due to gravity is the same at all times, even when the ball is at the top. So I'll explain that a little bit in a moment. The speed of the ball is the same at a certain height, whether the ball is going up or down. So here's my little parabola shape of a ball that I tossed up in the air. It is a parabola, so it's symmetrical. On the way up, I know I have a positive velocity, and on the way down, I have a negative velocity. I know I'm slowing down on the way up, speeding up on the way down, which means I must have a negative acceleration on both sides because it's gravity. The acceleration of gravity is always negative 9.8 meters per second squared. And that is always, which is what this little bullet point was trying to say. So a question that might trip some of you up is, what is the acceleration of the ball at the top? The acceleration is because of gravity. Does gravity just turn off because I tossed something in the air? No! 9.8, negative 9.8. What is 0 at the top? Went from positive velocity to negative velocity. It has to be velocity is the one that's negative. Velocity, or sorry, not negative. Velocity is the one that's 0. So please don't mix up the two. The acceleration of gravity is constant. It is always the same. Gravity doesn't just change because I throw something in the air or I put something on a ramp. Gravity is always the same. It goes from a positive velocity on the way up, it briefly stops to change direction, and falls to a negative velocity on the way down. Those are just telling me direction. So 0 is the velocity at the top, negative 9.8 is the acceleration because of gravity all the way through. Great. Example problem. A ball is tossed into the air. If you want, you can highlight tossed so you at least can identify it's a free fall problem. Technically, these objects are in free fall too because gravity is the only thing affecting them after it leaves your hand. That's why it's called free fall. Even though it doesn't seem like, oh, you're used to things falling down, they can fall up briefly until gravity forces them to change direction. So anyways, a ball is tossed into the air at an initial velocity. Love that. They just tell it to me. They make it easy. Initial velocity of 30 meters per second. How long does it take for the ball to reach the peak? That is something I will take into account here because I always know information at the top, at the peak, at the max height of a throw. So how long does it take for the ball to reach the peak of its toss? There's more questions. We will come back to them, I promise. So I'm going to write down stuff I know. Ball is tossed into the air with an initial velocity of 30 meters per second. I'm going to go ahead and make that positive because we have an object potentially moving in 2 different directions, up or down, and they just said tossed into the air, so I assume tossed up. How long does it take? So we are looking for time for the ball to reach the peak. Here's my trick. Here's what I like to do. We have something that's tossed up into the air and comes back down. We can always assume a couple of things, just like with your free fall dropped problems. I can always assume when something is being affected by gravity, its acceleration is negative 9.8 meters per second squared. I can always assume that if gravity is the only thing affecting the motion of the object. There is something else I can assume. I know the velocity at the very top of an object moving in a parabola. I know the velocity, I call it the velocity at the top, is 0. And I always love to write it down like this, okay? Velocity at the top can be plugged in for either initial velocity or final velocity based on what you know about the problem and what you need. For instance, this problem, we already have an initial velocity. I don't need to know an initial velocity, they tell me. So I'm probably not going to use it as an initial velocity. I will use it as a final velocity. It's not the actual final velocity of the ball, but I'm just treating it like it is so I can find out certain information. So let's think about it this way. The initial velocity is 30, and that happens at the beginning of the motion. If I treat 0 like the final, we are measuring from this point in the motion to this point in the motion. And what is the question asking? How long does it take for the ball to reach the top? That is specifically what they're asking for, that time for that motion. So that works out. Which equation am I going to use? I'm going to use the one without displacement in it because they didn't tell us anything about a height. I mean, they mentioned peak, but they didn't ask us to find any distance. They didn't give us a distance. So I'm just going to use this equation. You also want to be sure to keep track of positive and negative here. Every time you have an object potentially moving in two different directions, up or down, positive or negative, left or right, you want to be sure to label those so you don't mix things up and get a bad answer. So 0 is, speaking of mixing things up, 0 is supposed to be my final velocity. 30 is my initial, and that would have changed my answer. So be very careful when you do that. Times time. Be careful. You cannot add these two together. A lot of you are going to try to do that. Cannot do that. I'm going to subtract 30 from both sides. Work out some math. And then I get 30 divided by 9.8. Negatives cancel, which is great because I never want a negative time. I get 3.06, or to round to proper sig figs, 3.1 seconds. Great, that's part 1. Part 2, what is the ball's velocity after 6 seconds? So now we have some new information. I'll write it down in a different color. Instead of looking for the time, we are given the time. The time in this case is going to be 6 seconds. And now we are looking for the new velocity of the ball. So, new velocity of the ball is going to be my question mark. You could do some fancy stuff, and since you know the top happens at 3.1 seconds, and you know the velocity at the top, you can use all those numbers and subtract and find velocity, with the new time, and don't do that. My big rule is don't use numbers that I calculate. I am correct in this instance, so I could use this number, but I just want to use numbers that are given to me in the problem when I can. Sometimes you can't help yourself, just so I don't get multiple answers wrong because I made a silly miscalculation. So I want to avoid using that time if I can. So I'm going to use the original numbers they gave me. I know initial velocity, I'll just rewrite them so it's maybe slightly less confusing. Initial velocity is still 30, same problem. Gravity is still accelerating the ball at the same rate. And then we know the time, or at least we know the time we're looking at, is 6 seconds. So guess what? I'm going to use the same equation. Shocker. So final velocity is over here, 30 plus negative 9.8 times 6. Put 6 seconds. I don't know why I put the units for that one and not the other. So 9.8 times 6. So we have 30 plus negative 58.8. So my final velocity is negative 28.8 meters per second. Great. I should probably round that to 2 sig figs, which I didn't do on my answers. I can see down here. So final velocity or velocity at 6 seconds is about negative 29 meters per second. And then the last part of the problem you can see asked for the same thing, but 7 seconds. I'll use the same exact equation, but just plug in 7 seconds instead of 6. So if I do the math for that really quickly right now, I'm not going to work that out for you. I'm just going to show you something. I get about, I'm going to say final velocity, and I'm going to put parentheses 7 seconds so you know the difference. It's about negative 38.6, or I should round that to 2 sig figs, so about negative 39 meters per second, which, if you think about it, this acceleration, negative 9.8 meters per second squared. That means, I'll zoom in so I pretend to have some more space, 9.8 meters per second. So that means every second I add negative 9.8 meters per second to my current velocity. Each second, my velocity adds negative 9.8 meters per second to it. So if I go from 6 seconds down here, about 29, to about 39, well, negative 9.8 is about 10. So 1 second later, I should be going 10 more negative meters per second. So you could have maybe figured that out without plugging it in. Maybe. Okay, cool. Last example. A basketball player jumps up at a velocity of 2 meters per second. That's my initial velocity. How long is he in the air? Ooh, this one's tricky because it looks like it doesn't give us any information, like small bits and pieces. So 2 meters per second, time is what we're looking for. And, ooh, what else do I know? Yeah, that's the question. So he jumps up in the air and comes back down. He's still on Earth. Gravity is still affecting his motion and accelerating him at a rate of negative 9.8 meters per second squared. So I can always assume that as long as gravity is affecting the motion of the object. So now there's a couple of different ways you could solve this problem. How long is he in the air? I am not looking for just that time like I was in the last problem. I am looking for the whole thing. But it can be perfectly split in half because it is symmetrical. So there's a couple of pieces of information I know. I know velocity at the top is 0. I can always assume that, and I can always write that down. You can if you want to. But something else I know. The final velocity of this person, if he comes back to the exact same spot on the parabola, is negative 2. And that's something I forgot to mention on this slide. I'm going to kind of jump back. That's what they were saying about this symmetry in the motion, and the height, the speed of the ball is the same. At this point in the motion, the speed of the ball, let's say it's 2 meters per second. At the exact same point on the other side, it's still going to be 2 meters per second, but it's going to be negative instead of positive because they flip directions. So if it's 1 meter per second here, it's going to be negative 1 meter per second at the exact same point on the other side. Perfectly symmetrical. So, going back to this problem, I can assume his final velocity as he hits the ground, not after he hits the ground, not after he collides with the ground. Collisions are something different. We will do those in the second 9 weeks. We are just looking at how gravity affects the object. So his final velocity as he hits the ground, the last thing gravity does to it before the ground has a chance to affect the motion. His final velocity as he hits the ground will be 2, negative 2, the exact same speed on the opposite side. So I can use either of those velocities if I know how to use them. In either case, I'm going to use the same equation because I have lots of velocities and acceleration and I'm looking for time. So I'm going to do this equation, no matter which number I use. So I'm going to solve it twice. I know that's a little excessive. You can skip through if you feel like you have it or just want to see one version of it. But let's say the final velocity of the object is -2. Let's say we actually use the final velocity, the real final velocity. +2 plus -9.8 times time. When I subtract 2 over, I end up with -4. -9.8 times my time. We're going a little fast. You can pause me if you need some time to process the math. The time I get is 0.4 seconds, 0.41 seconds. So I'm going to do the same thing, but with the other number. And I kind of want you to pay attention because this does turn out a little weird if you use velocity at the top. But let's say we do use velocity at the top. We don't use the actual final velocity of the object. That means the initial velocity that happens here, and we're treating velocity at the top as the final, so we are measuring half of the motion. So velocity final equals velocity initial plus acceleration times time. We're pretending velocity at the top is my final. Velocity initial is +2 plus -9.8 times time. Still going to subtract 2 from both sides. Divide both sides by -9.8. I get 0.204 seconds. That's different. But if you think about it, I only solved for about half of the motion. So if they're ever asking for the whole motion and you use velocity at the top at all, know that you're only doing half. To get the whole motion, you just multiply by 2. 204 times 2 is about 0.408, which is what I got when I typed this into the calculator. So I just rounded to 0.41. So a couple of ways you could have gotten that answer. Whichever way makes sense to you, you should do. The velocity at the top thing you don't need to write down. It's just if you're completely stuck and you can't think of anything else you can assume, that is always true. At the top of the motion, the velocity is 0. You're moving up, then down. You can also assume at the same side on the other side of the parabola, but sometimes you don't always have it landing in the same spot, so you can't assume that always. Ooh, last question. How high does he jump? We are looking for delta y. You could also call it delta x, but we're being specific to direction. This is up and down now. How high does he jump? So we're still talking about the same problem, so there's quite a few things I can still assume, like the initial velocity of the object is 2, gravity is still accelerating the object at the same rate. I know how long it takes to get to the top, so I could use that number if I was correct. But again, I calculated it, so I kind of want to not use time if I can help it. So what else do I know? Well, anytime they mention height, peak, top of the throw, max height, I don't know, I can't think of any other ways to say velocity at the top becomes important here. You can assume velocity at the top is 0. So which equation would I use here? I would use velocity final squared equals velocity initial squared plus 2 times a times delta y. So I am going to, since I have initial velocity, I'm going to use velocity final as my velocity top. 2 squared plus 2 times -9.8 times delta y. Gonna have to do some algebra. Oh, geez. 4 divided by 19.6 gives me a delta y of 0.020 meters. So I'm going to show you one more thing. I know you want to be done. I want to be done too. But I'm going to show you what happens because some of you will make this mistake. Some of you will see this problem, and instead of using velocity at the top, you will plug in that final velocity, which technically is not wrong, but let me show you what happens. So I have negative 2 right here. That negative 2 squared becomes 4. I still subtract the 4 over. 4 minus 4, negative 4, yeah, 4 minus 4 is 0. 0 divided by 19.6 would give me a delta y of 0. Why did I get that? I'm going to draw this picture again. Think about the motion of his jump. He goes up and he comes down. At this location is where he has a velocity of positive 2, and at this location is where he has a negative 2 velocity. His displacement from here, from that speed to that speed, is 0 because he ends up back where he starts. So technically you were plugging in correct information if you use this number, but you're going to end up finding out that he lands where he started, which is not what they want. They want to know how high does he jump. What is the displacement from the beginning to the middle of the jump, right? Because that happens at the top. So anytime they mention height, top of the throw, anything like that, you should use velocity at the top, which is another reason why I like writing it down, to remind myself I know something happens at the top. Great, good luck. Do your practice problems, study, study, study. This can be an intimidating test for some, but not if you practice. Practice, ask your teachers questions. Okay, I'm done.